now we just saw about the binomial distribution. Now another there are a couple of other famous distributions, and I will just describe them briefly. Okay. So, the first one is called the Poisson distribution, and this is like a limiting value of the binomial distribution. Okay. So, like a limiting value of the binomial distribution. Okay. Let us to motivate it, let us consider that you do experiments over time. Okay. So, the idea is that there is some process, okay, or some process happening over time. Okay. The most common example is that of radioactive decay. Okay. So, where what you think of is you have a nucleus of a radioactive element, okay, and over some time it decays, okay, and each decay is one instant, okay, or one single process. Okay. So, in one decay one atom decays, okay, then later on some other atom might decay. Okay. So, now what you think of is you look at these processes over time, okay, and you might have one happening here, another one happening here, next one happening here, next one happening here, and so on. Okay. You might have, actually let me show this in red. Okay. So, the decay process takes place at various, each of these corresponds to one of these processes happening. Okay. So, if you have something like this happening, then you can ask what is the, so we can ask a question that in interval delta t, what is the probability that m processes have taken place. So, if this process is radioactive decay, then what is the probability that exactly m atoms have decayed in interval delta t, that exactly m. Okay. So, it is very important when you say m, you mean exactly m. Okay. And what we will assume is that the probability of any one process to take place P is equal to delta t by t. So, take place in interval delta t, t is total time. Okay. So, that means during each interval, okay, there is a probability that the event takes place, which is delta t by delta t. So, that means over this whole time t, okay, basically this process, all the I mean this process, the probability that will decay over this entire time t goes to 1. So, in this case now you can write the probability that exactly m processes have taken place as n factorial divided by m factorial n minus m factorial, just like the binomial distribution, and you have p raised to m 1 minus p raised to n minus m. Okay. So, where n is equal to t divided by delta t. Okay. N is the total number of intervals, okay, which is t divided by delta t. Okay. So, what you are imagining is that you are breaking up this interval of time from 0 to t into units of delta t. This is your t, and you are breaking it into units of delta t. Okay. Now we just go ahead and we say that n factorial okay. Now the basic idea of a Poisson distribution is that in each interval probability of process taking place is identical. Okay. In other words, if you think in terms of radioactive decay, then within each interval the probability that one particular atom will decay is the same, which is p. Now, the idea is we want to consider the case. Okay. So, we will make a few changes in this. Okay. We recall from binomial distribution that average value of m is equal to n times p is equal to n times delta t by t, okay. And we will call this as lambda times delta t, okay, where lambda is n by t. Okay. So, this is a notation. So, what you can do is that your mu or average value of m, this is mu is lambda times delta t. What we will do is we will try to eliminate t, okay, and write wherever we have t, okay, we will write it as n by lambda. So, we will write t as n by lambda. Okay. So, lambda is equal to n by t or t equal to n by lambda, and what you can do is that after some manipulations we can show that as delta t tends to 0, okay, as this interval becomes very small, okay, p of m can be written in the following form, can be written as lambda delta t raised to m divided by m factorial times e to the minus lambda delta t. Okay. Now, I have skipped quite a few steps in this derivation, okay, but the basic idea that we will use is that e to the minus lambda delta t is equal to 1 minus lambda delta t plus lambda square delta t square by 2 factorial minus lambda cube delta t cube by 3 factorial plus and so on. Okay. So, you use this infinite series. Now, what we will see is that as delta t goes to 0, okay, then you can truncate this to only some part. Okay. You can approximate this by only part of the expression, and that is what we are going to use in order to show that this is the same as this. So, we can say approximately equal to 1 minus lambda delta t as delta t tends to 0. Okay. So, once you use that, then you can show that this result and what you have here are essentially the same. So, with this we can so now that we have this result in place. So, we will just use this result p of m is equal to lambda delta t raised to m divided by m factorial e to the minus lambda delta t. This is called a Poisson distribution. Okay. And what are the properties? Average value of m equal to lambda times delta t. Okay. So, sometimes you can write p of m as a raised to m divided by m factorial e raised to minus a, okay, where a is the average value of, and average of m is equal to a. Again, this is something that you can show fairly easily. Okay. Now, what about the standard deviation? So you can also show sigma square is equal to a, equal to average of m square. Okay. So these are the two characteristics of this or two properties of this Poisson distribution, okay. And this is something that is fairly widely used. Let me just highlight these points. Okay. So this is another widely and you can use for example in radioactive nucleus decay. Okay. General this Poisson distribution can be shown to work for general so this is called a Poisson process, okay, where the important thing is that in any interval delta t. So, if you take any of these intervals delta t, the probability that the process happens is equal. Okay. So, probability that happens process is equal, and just using that you can derive this Poisson distribution. Okay. Next distribution that is extremely popular is what is called a Gaussian distribution. And this is typically for continuous variables. Okay. So, here p of x is written as is proportional to e to the minus x minus x 0 whole square divided by 2 sigma square. Okay. And what is this constant of proportionality? So, the first thing you can say is that to determine this constant of proportionality. So, you impose integral p of x dx, and the range of x is minus infinity less than x less than infinity. So, integral p of x d of x from minus infinity to infinity equal to 1. Okay. This is implies a, which is this factor that is there here, a, okay. And now you have integral from minus infinity to plus infinity e to the minus x 0 whole square divided by 2 sigma square dx. Okay, this is a Gaussian integral. Okay. So, this works out to be a times square root of pi divided by 1 by 2 sigma square. So, what this implies is that and this is equal to a times sigma root 2 pi. So, therefore, so this equal to 1 implies a is equal to 1 by sigma root 2 pi. Okay. So, p of x can be written as 1 by sigma root 2 pi e to the minus x 0 whole square divided by 2 sigma square. This is a, so average value of x is equal to x 0 and standard deviation of x equal to sigma. Okay. And what this looks like, this Gaussian function is it looks like a Gaussian distribution function. So, if this is minus infinity infinity, this is your x axis, p of x I have shown this axis. So, what is done is that you take some point x 0 and this looks like, this function looks like this, where this spread is equal to sigma, is of order sigma. This is the mean, okay. This is the standard deviation is a measure of the spread. Let's calculate the quantity called the full width at half maximum of P of x. Okay, so this is called as FWHM. Okay, so to calculate this, so P of x is maximum. So we can do this. We can see this P of x is maximum, and when it is, it's maximum at x equal to x 0. When x equal to x 0, then this quantity e to the minus x 0 square by 2 sigma square is e to the 0, which is 1. So this value is just 1 over sigma root 2 pi. So what you have to do to calculate the full width at half maximum is okay. So is calculated when P of x prime is equal to, now it will be 1 over 2 sigma root 2 pi. Okay. So when you have it equal to 1 over 2 sigma root 2 pi, okay, then what you will say is that 1 over 2 sigma root 2 pi is equal to 1 over sigma root 2 pi times e to the minus x prime minus x 0 whole square divided by 2 sigma square. Okay. So basically e to the minus x prime minus x 0 whole square divided by 2 sigma square equal to half. And if you take logarithm on both sides, okay, logarithm of half is minus logarithm of 2, okay, and so what you will get is x minus x 0, x prime minus x 0 whole square divided by 2 sigma square equal to natural log of 2, or you can write that x prime minus x 0 whole square equal to 2 sigma square natural log of 2. Okay. And this implies that x prime minus x 0 is equal to 2. We can just look at the width. So there are two possible values. So x prime minus x 0 equal to plus minus sigma root 2 ln 2. So that implies that full width at half maximum is equal to, so it will be twice this separation. So I can just write it as 2 sigma square root of 2 ln 2. Okay. Now natural log of 2 is about 0.69. Okay. So 0.69 into 2 is about 1.38. So square root of 1.38 will be about 1.19, and so what you get is about HM is approximately equal to sigma into 2.37. So essentially this spread at full width at half maximum is of order 2 sigma, is approximately sigma into 2.37. Okay. So in other words, it is proportional to sigma, and it is some small multiple of sigma. So sigma measures the spread of this distribution. Gaussian distributions are ubiquitous, that means you see them everywhere in sciences. Example is Maxwell-Boltzmann distribution of of velocities. Okay. This is one example of a gas. Okay. But there are several other examples, and in fact, what is important about distribution is that that if a distribution is not known, then typically we guess that it is Gaussian. Okay, this is a very important idea that is underlying lot of the things that we do. Okay. So, we also, I mean, for example, when you do your experiment, you calculate, you do your measurement many times. What you do by default is to calculate the average and the standard deviation. Okay. So, you are implicitly underneath that, you will be it turns out that you are assuming that your variables are distributed like a Gaussian, okay, with this mean and standard deviation, and in fact we use that to analyze to estimate the error. Okay. So, we will see that in the next lecture. Okay. But there is a deeper reason why Gaussian distributions are assumed, okay, and this has to do with something called the central limit theorem. Okay. So, the central limit theorem So, what this says is that suppose we have variables x1, x2 up to xn, okay, xn. So, these are different variables, okay, each satisfying same probability distribution and independent of each other. Okay. So, they are independent of each other and satisfying the same probability distribution, okay, such that average of any xi is equal to mu and sigma of xi is equal to sigma. So, each of them have the same average and standard deviation. Okay. Then the x is equal to x1 plus x2 up to xn, okay, the sum of these variables, okay, as n tends to infinity. Okay. So, if you have a very large number of variables, okay, as n tends to infinity, the sum of these variables, okay, x, okay, is a Gaussian variable with average x equal to n times mu and average sigma of n, sigma of x is equal to sigma divided by square root of n. Okay. So, in other words, I can write sigma x square equal to sigma square divided by n. So, this theorem basically says that if you have a large number of variables, okay, and these variables might satisfy any distribution, okay, but they should satisfy the same probability distribution and they should be independent of each other, okay, then their sum looks like a Gaussian variable, okay, and the important thing is that the sum of these random variables is a Gaussian. Now, you can, this seems a very obscure statement, but when you make any physical measurement, it is like making a number of small measurements, okay, and you are taking, and I said the sum is Gaussian distributed with this distribution. Okay. You can also take the average, and if you take the average, then okay. So, if instead of x we had x by n, okay, equal to x1 plus x2 plus x n by n, okay, we will have average value of x by n equal to mu, and sigma of x by n is equal to, it remains the same, that is sigma of x by n square equal to sigma square divided by n. So, basically if you think of any macroscopic measurement as average of lot of small microscopic measurements, then the Gaussian distribution is very natural. If you think of very large number of measurements, then things do look Gaussian, okay. And in fact, you can show this, okay. We can show that both binomial and Poisson distributions tend to a Gaussian distribution for large n. Okay. So, so the Gaussian distribution appears very naturally, and that is a distribution that we see, and that is the distribution that we used most often. I will conclude this lecture here. So, in the next lecture, what I will describe is the idea of error estimation. Okay. So, we will look at what are the standard estimates of error, and what I want to emphasize is that underlying the whole error analysis is the idea that your variables are somehow distributed like a Gaussian. So, I will stop here for now, and thank you.